and thank you very much for joining us here on a cold Tuesday or Wednesday evening. So this is the second National Climate Lecture of 2019. And of course, tonight I also want to welcome those of you who are joining us online, as this lecture is also being live streamed to the web. So we both have the physical presence and then, as I said, live streaming as well. So my name is Laura Burke and I'm the Director General of the Environmental Protection Agency, who are hosting the event tonight. And we are also delighted to have Met Éireann as a partner in hosting this timely and important event. So firstly, I'd like to welcome our speaker, Dame Professor Julia Slingo, to provide what promises to be a really engaging and thought-provoking lecture. So we're really appreciative, Julia, taking the time to come over to join us here. And of course, I'd also like to thank John Bowman, who will be our chairman for tonight. And for those of you who come regularly to the EPA climate lectures, you will know that really it wouldn't be a lecture without John, because for the many years that we've been hosting these lectures, we always have John, and it's always proved to be a really successful evening. So I think the two are combined. I should also say that the Climate Lecture Series is part of the Government of Ireland's National Climate Dialogue and Climate Action, and the aim is to create awareness, engagement, and to enhance motivation to act to address climate change. And I think if many of you, I'm sure, were watching or listening to RTE last week with the week-long programmes on climate and climate action, it really shows that there's such a huge level of interest and a desire to act on this important issue. And when you look to our role, the EPA's role in climate change, these include the provision of national greenhouse gas inventories, projections of future emissions, national implementation of the EU emissions trading scheme, coordination and support of national climate research, and so on. And these roles are central to informing and advancing climate actions in Ireland. And of course, we also work with the EU and UN partners on climate change, including representing Ireland at meetings of the Intergovernmental Panel on Climate Change. And the IPCC is the body that provides authoritative information on the science of climate change and response options through adaptation to its impacts and mitigation of its drivers. And the IPCC has reflected our evolving understanding of climate change from a discernible human influence to unequivocal warming of the climate system, with human influence being clear. So many of the co-chairs and authors of the IPCC fourth and fifth assessment reports have provided lectures here over the years, over the 12 years that this series has been running. And we're looking forward, as I'm sure many of you are as well, to the publication of the sixth assessment report. However, tonight we're delighted that Dame Professor Slingo's presentation will provide us with some insights on where she perceives that climate science is at and where it's going. And I'm not going to talk more about Dame Slingo's biog, because I know that John will give some sense of the expertise of our speaker tonight. The only other thing that I'm going to do is to say that this presentation, along with being broadcast live, will also be uploaded to the EPA web pages as an enduring national and international education resource, along with all of the previous lectures from the series. So I'd lastly just like to thank you all for attending here tonight and also for attending online, and to hand you over to John, who's going to introduce the format for this evening. Thank you very much.
Thank you, Laura. And just some housekeeping points first. Mobiles should, of course, be turned off. The fire exits are as marked, as are the bathrooms. It will be all live streamed, and if you wish to send a question in, it's hashtag Climate Lecture 2019. And we'll also have questions from the floor, and ask you, if you're making one, to give us your name and your organization, if any, or your area of expertise, if any, so we can spot the spin, if any. Before that, let me also just introduce our key speaker tonight, Dame Julia Slingo, who is best known for her tenure as Chief Scientist of the UK Met Office, where she was noted for breaking down the differences between climate and weather sciences and dealing with multiple meteorological challenges, including the highly disruptive Icelandic volcanic ash clouds. She's also the visiting professor at the University of Reading, founding director of the Walker Institute for Climate System Research, and among her many achievements, Dame Julia has served as a high-level scientific advisor to the European Commission's scientific advice mechanism, and particularly known for her passion for interdisciplinary research. The title of her paper tonight is Where Next for Climate Change, Where Next for Climate Science. Would you please welcome Dame Julia Slingo.
Good evening, everybody. I must say it's a great honour to be here and to speak to so many of you on my subject, climate science. I'm now retired, but I've been working on climate science since my early 20s. And you might think 40 years on or so, what's left to do? Well, there's an awful lot left to do, as I think I shall tell you. But let's start with Paris. And Paris 2015, some people thought it was a bit of a failure in the sense that we didn't get a really serious commitment, although actually over 190 countries did sign up to do something. For me, it was a massive success because it was the first time ever that the evidence of my science was accepted by virtually everybody. And so for me, you know, Paris 2015 was the end of the beginning for climate science. We'd spent 40 years or so, and I published my first paper on doubling CO2 in 1978, so yeah. It was, in a sense, the end of the beginning, and you might say that we know the Earth is warming. We know it's pretty well mostly due to us. What else is there for science to do? And of course, the Paris Agreement set a long-term goal of keeping the increase in global average surface temperatures below 1.5 or 2 degrees, but preferably 1.5 degrees. And in a sense, you could say, well, thanks, science. That's all I need to know. We just now need to go and engineer our way out of this problem. But of course, it's not as simple as that. And the place we were at in 2015 was already a pretty uncomfortable place. And it's worth just reminding ourselves that in 2015, the global surface temperature rise was already halfway to 2 degrees C. We'd passed the 1 degree C threshold. We'd only seen about a third of the global sea level rise that we think we'll see by the end of the century, whatever we do. And we'd already used, actually, 2/3 of the total carbon emissions to have a 66% or greater chance of staying within 2 degrees C. So we're already in a pretty challenging place. And when you look at it like that, you realize that actually climate science has got a lot still to do. And the first thing to say that actually, regardless of all the complexity of the things that we talk about in the IPCC reports, there are some big science questions that remain unanswered that will have profound consequences for our future actions. And they're very simple. Where does all the heat go? We know that increasing greenhouse gas concentrations is trapping heat in the planet, but where does it all go? Where does all the carbon go? We know that that not all our emissions stay in the atmosphere. Where does all the carbon go? And actually, crucially for this planet, where does all the fresh water go? And you might say, well, surely you've answered those questions in the 40 years you've had. And the answer is no, we haven't. But yet they're the bedrock, in a sense, of everything about our decisions on how to adapt to climate change and how to mitigate it. So I just want to go very briefly through these three fundamental questions and tell you why I'm still posing them. Let's start with, where does all the heat go? Well, this, of course, we've measured somehow or other, we think, where does all the heat go by using this iconic global surface mean temperature graph. And we use global mean surface temperature as a shorthand way of talking about global warming. But actually, when you look at this graph, it's wiggling around all over the place. And although our emissions have been increasing pretty well remorselessly, the surface temperature doesn't. And I got in a fairly uncomfortable place when I was chief scientist of having to deal with this thing called the pause. Because for about a decade, the planet seemed to have stopped warming. And you can imagine how delighted the skeptics were that this was happening. And they were all saying, well, of course, you know, you're just making it all up, and the warming that we've seen so far is not significant. Of course, now, fortunately, and we knew all along, that at some point the pause would end and temperatures would take off again, and so they have. But of course, the pause raised all sorts of questions about, well, where does this heat go? We knew, of course, that when we looked at sea level rise, which in a sense is a great integrator measure, and probably a better measure than surface temperature, that actually global sea level continued to rise throughout the pause. And of course, we know that the oceans take up 90% of the additional energy trapped in the planet. So if the oceans were still taking up heat, why did we have a pause in the global surface temperatures? Well, it's because the ocean is a fluid, it's very dynamic, and it has a circulation, just like the atmosphere does. And what was very clear was that heat was being taken from the surface and sequestered into the depths of the ocean through some big ocean circulations, something we call the Pacific Decadal Oscillation. So most of that pause was just actually the ocean dynamics doing something with that heat, and in a sense hiding it away from the surface, which again for me says surface temperature is not necessarily the best metric for talking about global warming. So here's the global mean sea level rise, and it's built up from two components. We always talk about, well, if you warm water, it expands, and certainly the expansion term as we heat the ocean is there, and it's the red curve, but actually the biggest contribution is coming from the increase in mass of the ocean from water from melting glaciers, and particularly Greenland, especially, and to some extent Antarctica. And so a lot of the heat is actually going into also melting ice, which is kind of bad news for this planet. And again, how well do we understand that? Well, I would say pretty poorly. And if we look at the, keep pressing the wrong button here, at a diagram from a report just published by the IPCC, a special report on ocean and cryosphere changes, this is their summary of the factors that influence future sea level rise. And I think this, again, really interesting to see where we have a good level of understanding, the three plus signs, and where we have a low level of understanding. So we know quite a lot about the winds over the ocean and how they drive ocean currents. We know less about the currents, and certainly we don't know an awful lot about how the heat gets mixed down into the ocean. When we look at the hydrological cycle and its role in sea level rise, which actually is surprisingly significant, we understand very little about that. And certainly when we get to the ice processes, calving, surface melt, basal melt from warmer ocean waters underneath the ice shelf as it extends out over the ocean, we understand very little about that. And so, you know, there's still a lot of questions to be asked about where does all the heat go in the cryospheric system, and what does it mean for the future of sea level rise. So, next question, where does all the carbon go? Well, we know that the global carbon cycle currently absorbs about half our emissions, and this is a time series showing above the zero line our emissions from fossil carbon and land use change, and below the zero line are the sinks, and finally what is left in the atmosphere. And we can see from this that the combined ocean sink and land sink take up about half of what we emit. We've known this for a long time. The question is, particularly the land biosphere, is will it continue to offset our emissions at that same level as we go into a warmer world? And we can even see in this diagram huge variations in the land sink, which are then reflected in the atmospheric concentrations, atmospheric loading really, from year to year. And this is all to do with the biosphere interacting with the climate. And there's a very nice example of this if we look at an event that happened fairly recently of what happened to the carbon cycle over land as a result of an El Nino event in the equatorial East Pacific. And this was actually emphasizes one of the great advances, certainly in recent years, of Earth observation from space. These are two missions that are actually measuring carbon dioxide emissions and even carbon dioxide methane emissions. So we're now being able to actually look at the source terms and sink terms. And this is an interesting picture because when you have an El Nino year, you tend to warm and dry places like Indonesia, Amazonia, and to some extent you warm and dry Africa. And what you can see here is that the impact of that climatic event was to dramatically drive some wildfires, some major wildfires over Indonesia that put out about 0.4 gigatons of carbon. It was also hot, and the plants, a combination of heat and dryness means that the plants don't grow so well, so they take up less carbon dioxide. It also means that warmer soils emit more carbon dioxide through respiration. And so the net flux, for example, coming out of Indonesia was 0.8 gigatons extra carbon, or less carbon being taken up by the biosphere, more carbon remaining in the atmosphere. And if you add all those fluxes together, just for that one climatic event, you get to something approaching just under 3 gigatons of carbon. And if you think about the sort of the biospheric contribution here, the land sink's about 10. So just those climatic effects had really a big impact on the ability of the biosphere to take up carbon. And if we think as we go into a warmer world, well, we're already seeing a lot of wildfires. Whether they're due to global warming, we don't know. But we think very likely there'll be more wildfires. There'll almost certainly be more drought. There'll certainly be more heat. So you have to begin to ask, where does all the carbon go in the future? It's a fundamental question because it will set our allowable carbon budget for our emissions, future emissions. And then, of course, where does all the fresh water go? Well, the water cycle, immensely complex. It's one of the most interesting parts of the Earth's climate system. It's what makes this planet habitable. And of course, water is essential to all life. And if ever there was something we need to understand, it's the water cycle. I've worked on it pretty well all my career, from trying to work out how clouds form, when they start to rain, what their radiative effects are. And so when we look at the whole of this issue about where does the fresh water go, from when it's evaporated mostly over the oceans, carried by the atmospheric winds, rained out over the oceans but also over land, returning to the oceans through the terrestrial water system, it's immensely complex. And so there's, for me, still a lot of questions about where does all the fresh water go. Once it's evaporated from the surface and into the atmosphere, how do clouds form? Where do they form? At what height in the atmosphere do they form? And all these questions come back to the fundamental issue that we still are hugely uncertain about what cloud feedbacks will do to the climate sensitivity of this planet. And of course, changes in rainfall, whether it's patterns, whether it's intensity or frequency, it will have very, very profound effects for water security and food security, and of course, the all terrestrial ecosystems. So where does all the water go is fundamentally important. And one of the big gaps that I felt was there for a long time is that where does it go in the land system? What I call, how does it get from the sky to the sea? So once it rains on the surface, where does all that water go? Of course, it goes into surface drainage, it goes into rivers and streams, it goes down into groundwater and eventually into major aquifers. But we have actually no way at the moment of knowing in the future where the water, how the water will move through our land system. And it means that actually we really have got to get the disciplines of meteorology and hydrology together. And we've been very poor at doing that. Just a little plug here that I suppose one of my last acts as chief scientist was to get the Natural Environment Research Council to fund a major programme on something called hydro-joules. Joules is our land surface scheme in our climate models, to get the hydrologists to come in and actually work out how to put the movement of water through the land surface and the land system in general, so that we can give better advice in the future on water availability and flooding and all those issues. And of course, this is slightly tangential, but actually, of course, climate change is all about exploiting ancient carbon. Somebody recently called it fossilised sunshine, which I found rather a nice way of thinking about it. But we've also been exploiting ancient water, and this is another example of really innovative Earth observation. This is the Gravity Recovery and Climate Experiment. So it's a clever satellite that senses changes in the gravitational pull of the Earth from changes in the shape of the sphere and what's in the Earth's crust and so forth. And one of the things that's come out of that is that you can get an idea of the major aquifers and how they're changing in time. And what this shows is that over those 10 years, 1/3 of the largest aquifers in the world are being depleted while receiving little to no recharge. And the big areas that we're sort of acutely aware of are, of course, in India in the Gangetic Plain, where the water table is dropping and dropping. And of course, the Middle East lives almost entirely, and North Africa lives almost entirely on borrowed ancient water. So we have got to get to grips with where does all the fresh water go. And so if we come back to this very fundamental measure that we always get to of this thing called the equilibrium climate sensitivity, a measure of how much we think the planet will warm with a doubling of carbon dioxide, it's all about knowing where heat, carbon and water go. And so we've still got this large uncertainty. This is a graph showing the 5 assessment reports right from the 1990s through to the 5th assessment report in 2013, and looking at what we think the equilibrium climate, what the climate sensitivity of the planet is. And actually, it's virtually not changed. And that's because we're still struggling with these very fundamental bedrock questions. And in AR5, we actually pretty much excluded the low end, but we also said actually there's a fair chance it could be higher than 4.5. And I'll show later on that some of the results coming in for the 6th assessment report, we're now getting climate sensitivities that are 5 or more. So as we build better models, as we understand more, we may be broadening the uncertainties and we may be shifting to more uncomfortable places. But it's all about knowing these very fundamental things. So that's the bedrock, and now I wanted to go on and talk a little bit about things that influence decision makers. And as I've said, we're exploiting ancient carbon, we're exploiting ancient water, and there's no doubt that we're taking the planet into uncharted territory, somewhere it hasn't been for a very, very, very long time. And it's hard to understand and know where we're going to go because there are no analogues for us, really. And so there's some very big questions keep coming up. And I've been doing a lot of work recently with the insurance industry, asset managers, bankers. And actually these next set of questions are the ones that we ended up homing in on as to how we're going to manage both the physical climate risk of climate change, but also the transition risk, the impact on businesses and industry and having to move to a low-carbon future. So I want to spend the rest of the talk just going through these. How well do we know actually today's physical climate baseline risk from extreme weather just due to natural variability? So we talk about the future and how climate change will change extremes, but actually I will argue that we don't even know what our baseline is today. And then, of course, if we do know what that baseline is, how will it evolve in terms of changes in frequency or intensity of hazards? Most of what we'll feel from climate change is not the slow trends, but is all about the volatility of the weather and the impact of extremes upon us, our livelihoods, our infrastructure. And then there's those questions that are a bit more out there. What are the longer-term risks of dangerous climate change, including potential tipping points? And then finally, what is really central to the transition risk question is how might new knowledge of climate and Earth system feedbacks affect the pace and depth of mitigation actions to stay within 1.5 to 2 degrees? Because I said, we don't really know the climate sensitivity very well. We certainly don't know where all the carbon's going to go. So how will new knowledge affect the trajectories that we're setting in place to try and stay within those targets? So let's start with the first question. And I thought, well, I'd put an Irish picture in. And this is ex-Hurricane Ophelia, which was a completely unprecedented event as far as we know. It was the most easterly forming hurricane in the Atlantic. And it made its way pretty well due north and ended up extratropical cyclone over Ireland and caused a lot of damage. And so it was kind of what we might call a black swan. So was it climate change? Could it have happened in the past? Well, possibly. And we know that bad things do happen in the past. And I'm very fond of this little story because this is Sherbourne Abbey in Dorset, which is where my brother lives. And if you go into the Abbey, there's a plaque on the wall and it reads, This monument was erected by Mr. Thomas Mansell of this town in remembrance of a great hailstorm, May the 16th, AD 1709, between the hours of 1 and 4 in the afternoon, which, stopping the course of a small river west of this church, caused of a sudden and extraordinary flood in the Abbey garden and green, running with so rapid a stream that it forced open the north door of the church, on the other side of this picture, displaced and removed about, and he's very accurate, 7,222 foot of the pavement, and was 2 foot and 10 inches high as it passed out of the south door. If we got an event like that today, we go, my goodness, this has to be climate change. So we have to be really careful. We need to know what our baseline is, particularly in where we live at the end of a jet stream and with a very volatile weather. So on to my flood risk story of the UK. So while I was chief scientist, it seemed to flood all the time, and it caused me a lot of angst, and I was continually being called up by the government to explain things. And of course, after the Lake District flood in 2015, which was exceptional, I have to say, I got phoned up by somebody, a minister in the government, and he wanted to know, how much rain could we get, Julia? What's a plausible worst case for UK flooding in the next 10 years? It sounds a really simple question. And I thought, my God, I don't know how to answer this question. But he said, and I need to have an answer in 6 weeks. Right? So, the first thing to say is that, is it climate change? So that's what you ask first. And here's a couple of graphs. The top one is winter rainfall in the England and Wales over the last 100 years, and this is the River Severn as an example. And these are good records. They're about the longest we have. And if there's climate change in there, I can't quite see it yet. What I can see is epochs of rain-rich and flood-rich periods and rain-poor and flood-poor periods, all from natural variability to do with things like the Atlantic multi-decadal oscillation. The other thing to say is that you can see there's some extremes towards the end of the record, and we've got these outliers, but we've got 2 or 3 in 100 years. So the observational record is much too short to characterize the extreme ends of the distribution. And when somebody comes to you, as they often do, and say, well, what's a 1 in 100 year event? You go, well, I've got less than 100 years of data, so I don't know. So what are we going to do? So we're going to go off into chaos theory a little bit. And Ed Lorenz, who said, one flap of a seagull's wings may forever change the course of the weather. And this is the idea that things happening at the very fine scales move upscale and alter your weather forecast. It's the basis of why we always do ensemble weather prediction now, and even ensemble climate prediction. But of course, the other thing it tells you is that the sequence of weather that we've observed, say, over the last 100 years is only one possible way that the weather could have set itself up. Because if we hadn't chopped down a few trees somewhere in the world or managed water in a certain way, we would have been like a flap of the seagull's wings, and the weather could have gone off in any course it liked. So what we observed was only one possible, plausible path that the world's weather could have taken. So I thought, well, actually, let's go off and think about, if that's the case, can we use multiple realization of today's weather from simulations to find unprecedented extremes, even for the current climate? And this assumes, of course, that your simulation is up to the task. And we had implemented some new models in the Met Office at that time, which gave me confidence that actually we could have a go at this question. And so if you do that, what you find is that there are lots of black swans, if you like, unprecedented events, if you have a large enough sample set. So this is an example of the distributions of southeast England monthly rainfall totals. And the black dots are the 35 observed winters for the current climate. Because the other thing you don't want to do is start looking too far back, because they're not analogues, because the CO2 forcing is not the same, and maybe the phase of the multi-decadal oscillation is not the same.
And I just wanted to put this in, because this, in a way, again, a tipping point or irreversible change. This is the Opgracia in western Iceland. It's on top of a volcanic mountain. And the first picture is, I think, from about the mid-80s, and then this one is pretty current. And what was very interesting was that in August this year, Iceland put a plaque on this mountain, and it's a letter to the future. And it says, Ok is the first Icelandic glacier to lose its status as a glacier. In the next 200 years, all our glaciers are expected to follow the same path. This monument is to acknowledge that we know what is happening and what needs to be done. Only you know if we did it. And this August 2019, and CO2 was at 415 ppm. It's an example of an irreversible change. Whatever we do, I doubt that Ok will ever get a glacier back. And then finally, I just want to talk about this question about, I suppose, our allowable carbon budget. And what about how do we find the right pathways for mitigation? And this is, again, a diagram that was taken from the IPCC special report on the 1.5 degree target. And it's a schematic, actually, showing the options available to us to try and stay within 1.5 degrees. And it's a very interesting report. I haven't really got time to talk about it today. But let's just, look at one or two things here. The black line is an idealized total emissions curve of the net amount of CO2 released to the atmosphere. And of course, what you can see is that halfway along, around about 2050, if we're going to stay with 1.5 degrees without really serious cuts in our gross emissions from buildings, transport, industry, and so forth, we're going to go into this territory of negative emissions. In other words, having to take carbon out of the atmosphere. And the way that that's considered how you can do that is through changing agriculture, forest, and land use, and also through bioenergy, so the technological carbon dioxide removal. All of those actually have an impact on both of those will have an impact on our climate, and of course, very much so on our natural environment. And so we've got a lot of choices here to make and decide which of those bits of the system we're going to balance. Are we going to cut more at the beginning so we have less of a negative emissions challenge later in the century? Are we going to be able to turn over our agricultural, food and land use emissions from being positive to being ones that take up carbon? That goes back to my question of where does all the carbon go? We don't know. But the question, I think, for me is how might new knowledge of climate and Earth system feedbacks affect the pace and depth of mitigation actions to stay within 1.5, 2 degrees? Because this report gives us several options. But there's a sort of assumption that actually what we know today about climate and Earth system feedbacks is going to carry through into the future. So these pathways that we're putting in place today to cut our emissions, assuming that there's nothing out there that could really make a difference. But of course there is. And I'll go back now to the iconic plot, I think, from the 5th assessment report that looks at the temperature anomaly on the vertical axis against the cumulative total CO2 emissions. And actually, it's pretty much a linear relationship. And what we can see here, these different coloured lines going up, depend on which emission scenario you follow. And if we do business as usual, we'll end up at temperature increases at least over 4 degrees, and we'll have emitted over 2,000 gigatons of carbon. And we can see what apparently our carbon budgets, allowable carbon budgets are from this graph. You can read them off if you want to stay within 2 degrees. But the problem is that I noted at the beginning, we are already 2/3 of the way to a 2-degree world, because our allowable budget, as in the AR5, was 790 gigatons of carbon, from what we knew then about where does all the carbon go, and we've already emitted about 550 gigatons of carbon. The trouble is that actually since that report, we've learned a lot more about Earth system feedbacks that we knew were out there qualitatively, but actually we hadn't had the science, the observations and the simulations to get a sense of how important they were. One, of course, carbon emissions from permafrost. There's a huge store of carbon tied up in the northern latitudes in Russia and Canada, in permafrost, which is gradually melting. And another one, which is that actually the functioning of the terrestrial carbon cycle requires knowledge of what the nitrogen cycle is. If there's not enough nitrogen, plants don't grow. It's quite simple. So those two are strongly coupled. And in fact, the nitrogen cycle may limit the efficacy of the carbon cycle. And when you put those into that diagram, for the different temperatures, the permafrost really comes into play if we get really warm. But even the ability of the biosphere to take up carbon through nitrogen limitations, all of that moves us over to the left in this diagram. So in fact, it already says that our allowable carbon budget is smaller than we had anticipated. And whenever we look in the Earth system at these things that we're not quite sure how it's going to work, whether it's methane hydrates, or whether it's, the impacts of climate change like wildfires on our allowable carbon budget, I think we have less room for manoeuvre than we currently think. So we need to know these things for mitigation. All that sounds terribly negative. And you might sort of say, well, come on, scientists, why are we here 40 years on from when we all started this? And you've still got all these big questions. It's because the system is so immensely complex, and it's because the pace of change is so fast, and it's because the requirements by decision makers and politicians and business are becoming really quite demanding, and actually they often want certainty when we can't give it them. And so it is a really difficult place to be. But I wanted to end with a friend of mine, and this is Pierre Sellers, who was a British climate scientist, and he and I did interact in the early part of his career. He actually worked on modelling the land surface, and he was one of the first climate scientists to put vegetation processes into the land surface models that we use within our climate models. But he'd always been a closet astronaut, and he got the chance, and he flew 3 times on the space shuttle. And I just need to wake my computer up. He was a wonderful man and deeply concerned about climate change. And he died of pancreatic cancer at the end of 2016. And when he got his diagnosis a year earlier, he wrote a really very moving piece in the New York Times about his diagnosis and the fact that he wouldn't live as he had hoped to see what we would do about the climate change problem. And he wrote, "New technologies have a way of bettering our lives in ways we cannot anticipate. There is no convincing demonstrated reason to believe that our evolving future will be worse than our present, assuming careful management of the challenges and risks. History is replete with examples of us humans getting out of tight spots. The winners tended to be realistic, pragmatic, and flexible. The losers were often in denial of the threat. And it reminds me always of, for at least the first 6 years of my time as chief scientist, of having the battering from the skeptics and those who wanted to take me to court for misleading the government on climate change and so forth. But we were realistic, pragmatic, and flexible. We have to be that. And he goes on to say, as an astronaut, I spacewalked 220 miles above the Earth, floating alongside the International Space Station. I watched hurricanes cartwheel across oceans, gigantic nighttime thunderstorms flash and flare for hundreds of miles along the equator, and the Amazon snake its way to the sea through a brilliant green carpet of forest. From this God's eye view, I saw how fragile and infinitely precious the Earth is. I'm hopeful for its future. And I guess I am too, because one of the great things about climate science is it's given us this window into the future. If we're forewarned, we can be forearmed. And I think what climate science has done is it's forewarned us. And so it's up to us now to be forearmed and work out what we're going to do. And so at the end of the day, climate science continues to be essential. We've so much more to do. And it's all about helping us to live safely and sustainably on our planet. So thank you very much for listening. And I hope that some of it was useful, challenging, and keep following the science.
Thank you very much. Dame Julia Slingo. Can I call you Julia?
Yes, you may.
Yes.
Please do.
Now, you've probably answered this question, and I was surprised by your final point. Are you saying that you are optimistic?
Yes. Because we're a very ingenious species. And I think that we will work out the technologies, and we will work out how to change our lifestyles to deal with this problem. And in fact, actually, if we just look at the past year and the massive change in public perception and in this understanding, not just of climate change, but of our role in the environment and what I call Earth stewardship, has been massive. And hopefully we'll do it in time to cause not too much damage. But
there are a lot of tipping points.
There are a lot of tipping points, and some of them on that diagram I think aren't really there, to be frank. But some of them are. So, yes, we have to keep at it.
And when you say that this past year, it strikes me that David Attenborough's impact and then some of the images of the plastic on the sea, on the seabed and in the gut of these fish, that was a really big point, wasn't it?
Yes, and actually,
A shocking point.
yes, and I think, that was more about the damage that we're doing to our environment. But I'm quite comfortable with that, because this whole, the importance of what I call Earth stewardship, climate change is a small part of that. And there was a very interesting and very important report that came out earlier this year on biodiversity and ecosystem services, which was, I think, actually, for me, in some ways, more frightening than climate change, which was to do with the damage that we're doing to the natural ecosystems and the whole business of extinction of species and all of those, which of course Sir David talks about. And it doesn't really, for me, it doesn't really matter whether that's climate change or not, because all of this is wrapped up in actually stewarding the earth and taking care of the earth, which I think young people kind of get now. And plastic was a good example.
Also seen the young people, isn't that right?
Yes,
Recently.
yes.
Can we have the lights, please, a bit more so we can see who is suggesting? That's more headlights in our eyes. Yeah, that's better. Now, I'm going to prioritise those who have coveted the microphone and physically have the microphone. They'll be prioritised. So if I call you in, get one of the microphones and I'll go to you. Yes. And if you give us your name first.
Hi, how are you? My name is Aisling Greeley. I am a deputy school principal, but I'm here tonight just in the role of a very interested and concerned citizen. You referred in your lecture to the Gulf Stream, and we know it has a really huge impact on the climate here in Ireland and, of course, in the UK. Just going forward, how do you feel that climate change will impact on that? Thank you.
Right, so the Gulf Stream is part of something we call the Atlantic thermohaline circulation, and there's been in the past a lot of concern about would that circulation collapse as the planet warms. I think the evidence now is that it won't, at least in the current century. I mean, you'd have to have quite extreme warming for that to happen. It may slow down, but actually the impacts of that will be very minor compared with the impact of global warming. So, I mean, the Gulf Stream is not going to go away in a hurry.
Yes, back here, yep.
Paul Price from Dublin City University. Science looks at a range of uncertainty or confidence range, but insurance, you've been talking to insurers, talking about the extremes, obviously, and what's the dangerous end of that risk. Can you talk a bit about your experience of conveying risk to the public over time, and how that's changed, if it's changed?
Right, yes. I mean, I don't specialise particularly in communication issues, but I think actually, I think we've failed in communicating what we know about climate change by couching it always in uncertainties, and then more recently in probabilities. And actually, I'm really quite interested now in whether we can tell some stories, because I think stories that are rooted in the science give people access to the science, because they can relate to a story. You can personalize it. Indeed, I think, you know, that some of the work that we've been doing with actually the government and actually internationally using this synthetic events storylines has been very powerful. So I think, you know, we're coming to a time now where actually we should be thinking about not necessarily always emphasizing the uncertainties, but actually using things that will stress test the system a bit more. And when we talk about extremes, we really want to know actually a worst case scenario often. So let's find some. And we know that these simulations have some pretty unpleasant things in them. If we're confident that the simulation is robust physically, then we should stress test some of our systems, our infrastructure or other things, our homes, based on some of these narratives of particular events.
But it is in the nature of science to be uncertain and to test and
Yes.
test. I mean, that is the intellectual output.
Of course it is, but I mean, we're in a position where actually we don't have that luxury.
So you're talking about, and it often strikes me that this is not popularly known, but the precautionary principle.
Absolutely.
And that's at the heart of this sort of policy making.
Yes, and
Do the politicians understand that? Surely it should be more of the normal vocabulary
yes,
of
and
policy making.
Yeah, and that's why I think that actually always talking about negative words like uncertainty rather than confidence, but also actually picking out, as we did with the flood risk story for government, was doing something that actually gave a meaningful stress test in a way that they could understand and make a decision around. And, you know, if you take some more of the worst case scenarios, I think that's a fair precautionary principle, rather than sticking in the middle of the distribution. So I think we have to change our language and the way we present our science.
And what is your view of the politicians with whom you have dealt in general? They're on a 5-year cycle about the next election, so policy making is going to be influenced by that, is it not?
I think that's true in the past, but of course I'd say it's not true anymore. And it's been remarkable to see with the election we've got coming up shortly, how climate change is among the top 3 or 4 issues. I wouldn't have guessed that a year ago, but now it is. And yeah, I think we've just moved to a different place. And I also think that actually if you look at what's now being funded through the science budget, certainly in the UK, is really tackling some of this head on. I mean, we're funding technological advancements, research and innovation for things like batteries.
Are you worried though about what's happening? I mean, what damage has Trump done?
Actually, probably less than we think. Because when you get down to the state level, the majority of the states in the US get climate change, and they are introducing policies at the state level, and they're just ignoring Trump. And although he's pulled out of the Paris Agreement, that doesn't mean that the US isn't doing something there. There's a lot going on.
And states are very important.
Absolutely.
Yes.
Hello, the name's Howard Lenane. I'm an assistant filmmaker. Just, Julia mentioned the fact, I told a very interesting idea of telling stories, what we could be doing based on the science, and you mentioned dealing with worst-case scenarios. But a previous questioner, deputy of mistress, I think, of a school, deputy principal in the central area, I wonder what she would feel about that. There was a survey just published in the Irish papers yesterday or the day before about the anxiety and stress that school people around their school children, if they start hearing all this stuff, and only the worst-case scenarios, we've only 12 years, I think it's 11 now, or whatever, according to one prognostication, and this is going to put them under worse stress. Could we tell positive stories for them at least, so that they come out positive, thinking up ideas of how we can counter things, so they keep at least working on their books and trying to qualify at something, or, you know, why would... It reminded me of a 60s song, I think John Bowman might remember it too, from the radio at least, and there was this constant refrain in an American song, "You won't believe we're on the eve of destruction." It was one of these anti-Vietnam counterculture songs. Why would you work on anything if you were a child when everything is bad? That maybe for them we could tell positive stories on that, maybe.
Yes, I mean, it's a very good point, and I think actually if you're thinking about government or industry, actually they do need the worst case, because they need to stress test their system. When I go and talk to school children, which I do quite often, I always talk about what you can do. I mean, it's not a nice story, and let's be clear about that. We know it's not a nice story. But actually, there's something that everybody can do. And it doesn't have to be just about turning the lights off at home. It's all about actually our lifestyles as well. And so we talk a lot about recycling and reusing and, you know, clothing, because actually clothing's quite a big problem besides plastics. And, you know, food and what sort of food you eat and all these sorts of things. And actually, they find that really motivating. So they know that there's bad things out there, but you have to give them access to action. And so that they can go away in groups and think about, what am I going to do about this? And I can see the deputy head nodding. And you know, and it will, these things will make the world a better place, for sure.
Yes.
Peter Thorne, Maynooth University, late of Yorkshire. I'm not going to ask you about Climate Gate, don't worry.
That's all right.
But obviously 10 years ago we spent a lot of time, over 3 weeks, together on that. I was going to ask about the new models, the CMEP 6 models for the 6th assessment report, and about a third of those, as you noted, are going much more sensitive than the others.
That's right.
And I wondered whether you had a view whether that was resolution, processes, forcing, or what it is that might be underlying that.
I think it's still a bit early to say, but my sense is that it's back to clouds again. And the low cloud feedback and the brightness of the clouds. And so we've got, if you're a scientist, the aerosol indirect effect coming in. But it's very interesting, actually, that a number of what we would regard as the leading models in the world are coming in with climate sensitivities in excess of 5. So we have to look at this really seriously. Yeah. So I think that's what's going on.
Somebody here in left.
Hello, my name is Thomas Sarkovic, and I'm with Business in the Community. Governments and businesses have all now committed to net zero emissions, and I'm not a scientist, but is there a scientific definition of net zero emissions, and is that possible? Thanks.
I don't think I can answer that question. That sounds a bit outside my comfort zone.
Well, we've had many different expertise on that panel, so you're forgiven. Yeah, my wife tells me the second three most important ones are I don't know.
It's a multifaceted question, actually. Yes.
Yes, somebody here.
Hello, Sinead Flappen from RPS. I'm normally very much a sustainable transport advocate and cyclist. On this occasion, I'm just going to dare to ask a question about flood defence and erosion defence. And it seems that you have a very positive viewpoint, which is lovely to hear, or you're hopeful at least. And just thinking in terms of, obviously, with sea level rise, we have to consider our coastlines, particularly in Ireland, where we have an increasing population, and the risk of losing land is not a great thing. Look at the southeast of the UK, and I'm just wondering what you think of, how far do we go to defend our shores, and at what stage do you think about relinquishing it to the sea to allow nature to take its course? Like, do you think that's giving up, or should we be looking more strongly at flood defence? For example, what's your view on the southeast of the UK?
I think, these are difficult questions. It's all about cost-benefit ratios, I suppose, at the end of the day. What do you give up on, and what do you try and protect? And I think there's no single answer, as it depends on, what assets you're talking about. We will have to face sea level rise, and we will have to defend some parts of our coast from that, but other parts we may well, as you say, have to give up with them. And a very iconic example is this little Welsh village, Sherbourne, in mid-Wales, actually where I used to go on my summer holidays when I was a small child, which is now, they're saying, probably will be impossible to defend. I think it's worth remembering, that just here's a little reminiscence of the Paris meeting that I attended, and the low-lying island states, which are, of course, facing this already. And I sat on a panel with the president of Kiribati, which is one of the ones that's already being regularly flooded because of sea level rise. And he talked about preparing his population for migration with dignity. So it's about making sure that when the time comes and they do have to leave, they go skilled and able to go and be worthwhile citizens wherever else. And I think that's about thinking in adaptation. Some of it will be about preparing ourselves to let nature take its course, but make sure that we're prepared in a way that allows people to, as he said, migrate with dignity. And that's part of, early warning and all of those things allow people to take some actions where they're in some control of their destiny, which for some people in the world, they will not be.
Yeah, somebody with the microphone here.
Yes, hi. It's Paul O'Connor, JP Morgan. So my question is, if you had all the policy levers in front of you and money was no object, what do you think that we should be focusing on to actually provide some solutions to these problems? Should we be focusing on emissions mitigation, adaptation, more research, a mix of everything? What's your sense of where the focus should be? Thank you.
How long have we got? Not long enough to answer that question. Obviously, we have to seriously invest in technologies for a low-carbon future, and that means changing our energy supplies, looking at our agriculture and food production systems. As a scientist, I would say, please give me more money, particularly more supercomputing power, because the progress of climate science has been absolutely determined by how much compute power we have. It's quite simple. Give me a massive computer, I can tell you all sorts of useful things. I think it's a mix of everything, actually.
And what do you mean by a massive computer? I mean, one of the points about computers over the past 30 years is that they now cost, say, for sort of 300 or 400 pounds, you can get a computer that is kind of 1,000 times more powerful than one that used to cost 3,000 pounds. Isn't that true? I mean,
it's amazing, yes.
Amazing.
No, I mean, yes. Well, I mean, when I was chief scientist, I put a bid into government for our next supercomputer, and it was well over £100 billion, and we got 97 million. And it does 15 petaflops, which is 15 floating point operations per second, 15 peta of those, so that's 10 to the 15. It's a massive machine, and it stores petabytes of data. And even that machine, we had to build a new computer hall for it. Even that machine was not really what I wanted, because we know that if we can simulate the weather and climate at kilometre scale, as I showed that we've done for Great Britain and Ireland, actually, the United Kingdom and Ireland, that actually it tells us radically different things. But you need what we call an exascale machine to do that. And we're into that whole discussion now about, well, what does the chip technology, these things eat power, so we've got to look at different ways well, the chips have to be different. We're going to have to re-engineer all our codes. We're going to have to do it, though, because actually we need to get these simulations down to that sort of scale that I showed for those examples of flooding and high winds, because that's the information that decision makers need. But yes, 97 million was what I got, and I understand that the next one might be twice that, so who knows?
Yeah, somebody with the microphone, already in their hands. Yeah, can you ask people with the microphones to favour those who might ask the next question? Yeah.
Hi, my name's Kaylee. I'm a climate journalist, and I love the point that you made about stories. And I was just wondering, what stories could we tell better, and what stories are we not telling? Thanks.
Well, depends what you mean by stories, you see. So for a decision maker, you would do something like the sort of story I said, where we stress tested something. But actually, I'm very keen on the involvement of the arts and humanities in all of this, and whether we could, for example, tell stories about what the world might be like for a child growing up in the 2050s. We could tell that story. It would be really, in different parts of the world. So if you're an Inuit child, I think the story would be very different for a child growing up in 2050 than a child that's growing up today. So there are all sorts of possibilities that we can think about. Does that answer your question? Yeah.
So we can tell children's books and bedtime reading. you can put
Yeah.
messages in there that
Yes.
are, yeah, good.
And not all of them will be bad, actually.
There's
That's
this
what I
marvellous
see.
book, which whether climate change is included in this, I'm not certain, but I certainly used to enjoy reading it to my children who were not want to listen, which is a long time ago. But it was called, I don't know if you know it, the Butter Battle Book.
No, I don't know that one.
Dr. Seuss book.
Oh, it's a Dr. Seuss
it's
book, is
actually
it?
about
Yeah.
racism, because the whole arms race was based on those fighting one another. One lot wanted the bread with the butter side up, and the other wanted the bread with the butter sides down. And they're both building arms to defeat one another in the field. But it's a marvellously funny book, and yet if you're reading it, you're enjoying it, and the child is enthralled by it because they see the nonsense of it and so on. But anyway, some such books, yeah.
Thank you very much for a very interesting and informative overview of where we're at. I have a question which relates to a comment you made after you actually sat down when you made the point about the report on biodiversity.
Pardon?
The report, you made a comment on the report on biodiversity that came out earlier this year, and you said it was highly significant.
Yes.
My question would be, to you, as someone who clearly is interested in interdisciplinary approaches, would be if one were to treat equally and in tandem biodiversity and climate change, what do you think would be the most important headline changes that might now need to be thought about as ways forward, changes in the sense of steps forward compared to Paris 2015, by bringing biodiversity and climate change in joint focus?
Gosh, I'd like to see us do that, I have to say, is to put the international IPBES's report, which you may want to see, and it emphasizes that pollution, land use change are major factors, and then you add climate change. I would like to see those two things put much closer together, because they play off each other, actually. If you did, what would be the most important? Well, I mean, one has to sort of still think about Amazonia and the removal of the rainforests as being perhaps the iconic symbol of both land use change, man's destruction of habitats and so forth, and biodiversity, but also, of course, a huge climate change issue from the point of view of the carbon budgets, and of course from the point of view of the local climate. But I think the more we actually look, I mean, if you go back to 2015, I just talked about Paris, but actually there were 3 reports that came out in 2015. One was Paris, the second one was the Sendai Agreement on disaster risk reduction, which was also very important. And then there was Sustainable Development Goals. And actually climate and weather and that, they weave their way through all of this. And I think the more we look at things in this more holistic way, I think we have to do that if we're going to actually get to where we need to be in the next decade or two. We have to look at this, as I use the phrase, stewardship. But actually I found the statistics in the IPBES report, I didn't include the slide in the end, but actually they were quite frightening. And in many ways, for me, more urgent, needs to be dealt with more urgently in some respects than climate change, which...
We take another 3 questions. Yes, question down here.
Hello, my name is Dorothy Maxwell. I'm an environmental scientist. Found your lecture fascinating. Thank you. My question is, for the next UN Climate Summit, what do you think we absolutely have to get out of it to keep us moving forward?
Well, I suppose we would like, I mean, there's also a stock take coming up as well. after Paris. So in 5 years we have a stock take, which is coming up next year, I think. I think that's right.
Yes.
And I mean, that will be very interesting to see the degree to which the national commitments have got anywhere near what people were committed to in Paris, regardless of what the US is doing, but, you know. And I think just to reinforce, I mean, I think again, the public perception and the science has moved on, and the evidence base in terms of damaging extremes and wildfires and all those sorts of things that we see day by day now, something going on that's somewhat unprecedented. I think, you know, the politicians will be under enormous pressure to increase their commitments and to invest in the technology to deliver those commitments. And I think that's what we need to be seeking.
When you listen, when you watch the news on television, if you take Venice, if you take Sydney, if you take York.
Absolutely. I mean, you know, and the other thing to say is let's not forget that in Paris, actually, there was also a commitment by the developed world to support the developing world through adaptation, resilience measures. And again, another really important report that came out a few weeks ago was the Global Commission on Adaptation, and which has actually sort of measured the return on your investment today in adaptation measures. And some of the returns are very high indeed. And so I think, you know, we need to bring into the discussion actually adaptation. And they talk also, which comes back to the IPBES report, they talk about nature-based solutions to a lot of adaptation now. So a good deal for nature and all those sorts of things. So I think one of the other things we'll need to think about is there were commitments in Paris by the developed world into a fund to support the developing world. How far have we done that? What are the actions we could now take on new evidence on adaptation that we should just get on with? Regardless, you don't need to know the fine detail to know that we have to adapt. So where should we should start?
Yes.
Hello, I'm Tara Manigo. I'm a student of the Masters in Climate Change in DCU. The UK has always been a pioneer in terms of climate science and also a huge contributor to the whole discussion on climate change. How worse off do you think that the European Union will be in a post-Brexit scenario?
The European Union? Well, I hope that if we do Brexit, which is probably quite likely, that the collaborations in science, which actually have been very, very strong indeed in my field, we've really pushed forward a lot of science together with the EU, that will continue to do that. And, you know, I think you're right that the UK has always been a leader way back in Margaret Thatcher's time, and even prior to that, we've always led on the science and led on commitments, actually, with a climate-first country to have a Climate Change Act. And
on Venice, leaders. Cambridge
yes,
is a terrific leader.
yes, yes. So I don't see that changing, that I think we see it so high in the political agenda. So I'm hope, you know, and scientists will always collaborate, and I hope we can find a way forward post-Brexit to still have these fantastic collaborations with our European partners in climate science.
Yeah.
Thank you. Eileen McDermott, Wing Foundation Ireland, and I'm also a teacher. And thank you very much for that terrific talk. I'd like to know Dame Julia's opinion on the role of education for sustainable development, within the curriculum so that all children are prepared and are knowledgeable about what is happening, and also that they don't suffer from eco-grief and eco-anxiety, that they learn in a knowledgeable, hopeful way, but also the futures that are, the changing work futures for our young people as coming about as a result of climate change, to be hopeful about that. Thank you.
Well, I'll just agree with you, really. And I mean, I go back to Pierre Sellers' words that there's no demonstrated reason why the future should be worse than the past, provided we manage the risks appropriately. And I think, you know, we've already talked about how to engage with young people, and actually sort of, you know, well, the future will look different. I mean, if you go back 20 years, you know, we had no idea what our world would be like today. But I think, you know, just coming back to all the things we can do to be sustainable, yeah, I agree with you.
One final question here, which I know is
Michael O'Donnell, I'm a retired scientist. In your answer on whether you were optimistic for the future, you mentioned technology, that you expect technology to help us cope. I'm wondering how you feel about the suggestions on geoengineering that have been floated in recent years, whether you might think that they're too risky to try, but also whether you included any of these possibilities in your climate projections.
Right, so geoengineering is, I mean, let's make a distinction. There's carbon capture and storage, which was in actually those pathways that I talked about at the end, where you go into negative emissions. That's about capturing carbon. But the other one is what we call solar radiation management, which is all about trying to reduce the amount of energy from the sun that enters the planet and therefore sort of offsets the warming from greenhouse gases. And I have always had a very deep concern about those sort of possibilities, in the sense that we've already geoengineered our planet. We've done it quite simply by putting lots of carbon dioxide into the atmosphere, which is a well-mixed gas, chemically inactive, and quite a simple forcing of the climate system. And yet the response of the system has been incredibly complex, and we still don't understand, as I've already shown, what a simple forcing like increasing the carbon dioxide concentration uniformly in the atmosphere is doing to our climate. So when somebody comes along to me and says, well, why don't we geoengineer the clouds or put lots of reflective particles up into the stratosphere, you kind of think, you know, we can't do that unless we've done due diligence on the response of the climate system. And so actually, as scientists, we've been doing that. We've done these experiments of looking what happens, and actually the results just tell you yet again that the response of the system will not be just simply to reduce the global mean surface temperature, but to actually change the regional climate in some parts of the world in a very undesirable way. So they're in my view, irresponsible, and we should never consider doing them. Again, the other aspect of solar radiation management is that you have to keep on doing it. And as soon as you stop, within a decade or so, you'll be back on the trajectory for global warming that you would have been if you'd not done anything. And you will have already potentially put some systems through a tipping point. And so, yeah, we do due diligence on it, but I am very, very opposed to it personally as a scientist.
On that point, there are a lot of questions still in the room, but I would like to thank on your behalf Dame Julia Slingo for her outstanding and thank you also for being such a good audience and such a curious audience. on the web app. I would particularly suggest that to geography teachers, I know they were letter in the newspaper this morning about the need for geography not to be downgraded in any way, but there are so many other disciplines in the school room. I know that the benefit from this goes well beyond geography, but there are sound bites or answers to some of these questions which would make a great talking point in class. If you just take some questions from the archive